right, good evening. My name is Paul Shand. I'm the head of the physics department here at UNI, and welcome to the 2025 Begeman Lecture. This lecture series is made possible by the generosity of the Jordan family. Richard Jordan and Frances Jordan are the grandchildren of Louis Begeman, the first head of the physics department when UNI was Iowa State Normal School. Begeman, under the supervision of Nobel Prize winner Robert Millikan, carried out the first accurate measurement of the charge of the electron using water droplets. Richard, who celebrates his 95th birthday this month, is unable to make it to the lecture series this year. Still, let us applaud Richard for his immense positive influence on the UNI physics department. The 2025 Begeman Lecturer is Dr. Philip Rescherm. Dr. Rescherm received a bachelor's degree in physics with a minor in music from MIT. He holds both an MA and a PhD in physics from Harvard University. After his PhD, he spent 3 years as a postdoctoral fellow, then senior research scientist at the Joint Quantum Institute in College Park, home of the University of Maryland. He was subsequently hired by Indiana University as an assistant professor of physics, and he now holds the rank of associate professor. Dr. Rescherm has been awarded many millions of dollars in grants for projects in quantum science and technology from the National Science Foundation, the Department of Energy, the Department of Defense, and the Gordon and Betty Moore Foundation. He comes highly recommended by last year's Begeman Lecturer, UNI's own Dr. Justin Bonnet. The title of the 2025 Begeman Lecture is Making Heads and Tails of Quantum Information Science. This is our contribution to the International Year of Quantum Science and Technology, which most of you probably don't know. Please join me in welcoming Dr. Rescherm to UNI.
All right, well, thank you so much for everyone to be here. Thank you so much to Paul and the rest of the faculty in the physics department, all of the students that I've met, for all of your hospitality and great conversations, and I've really enjoyed my time here and visiting today. And so what I'd like to do for tonight is to give you a little bit of an insight into some of the work that we do in my lab at Indiana University, and also that's being done in the field at large, in this field of quantum information science. And I think that a lot of people who are paying attention to tech news out there, certainly quantum has been one of these topics that is all over the news, and there's a lot of buzz about quantum. Right, so just a few headlines that I've pulled. So we have that Intel is building a quantum computer, a quantum processor. We have IBM. We have Honeywell, now Continuum, that's building quantum devices. We have Microsoft. We have Google, all of whom are grabbing all of these headlines about their development in quantum information science. And like anything else, whenever there's buzz about a whole bunch of words, and quantum is one of those words, everybody tries to get in on the action. Right, so with a couple of additional Google searches, I've found that, for instance, we now have quantum dishwashing detergent. We have quantum batteries. Apparently, there's this quantum boat paint. And apparently, I've been taking vitamin C wrong my whole life, because there is now quantum vitamin C. All right, so with all of this development in quantum, with all of these kinds of claims of things trying to say that they are quantum, I think it's really important to distinguish what do we mean by quantum and what is not quantum. And so one of the big goals for this talk, goal number one, is to really describe what is it that makes quantum unique. Okay, and very specifically, what is it about quantum information science that is interesting, and what is it that quantum information science can do that's new compared to what it is that we could only do previously. Right, number two, what I'd like to do is to summarize what are some of the state-of-the-art developments in quantum information processing. Quantum information processing, quantum information science, this is a rapidly emerging and growing field, and there are lots of different sub-disciplines within this, and so I wanted to touch on what are all of the different aspects of quantum information science that might be out there and why we all might be interested in them. And then finally, I'd like to spend a little bit of time talking about some perspectives on what are the future applications of quantum information science, where this entire field is going, and approximately how long I think it's going to take us to get there. And I think that the journey in talking about quantum information science begins maybe all the way back in the 1950s. And this is a direct quote from Richard Feynman, Nobel laureate in physics. And what Feynman pointed out, 50 to 70 years ago or so, is that, this is a direct quote from Feynman, that when we get to the very, very small world, say circuits of 7 atoms, we have a lot of new things that can happen that are not classically accessible. Okay, so these are completely new opportunities for design. And what enables those new opportunities is because atoms and particles that are on the very small scale behave nothing at all like we're used to in the classical world. And the reason is because they obey these laws of quantum mechanics. Right? And I think it's kind of interesting that Feynman here in 1959 is talking about, in particular, circuits of 7 atoms. And just for fun, here's a picture of 7 atoms from my lab. And we'll talk about that in a little bit. But what you're looking at is an image of 7 atoms that I've levitated inside of a trap. And we can shine lasers at those atoms, and we can take pictures of atoms. Okay, so here's a circuit of 7 atoms. And as we go forward, I'll tell you what we can do with circuits like this that we can't do classically. All right, so I teach quantum mechanics at all different levels. I've taught it to undergraduates. I teach a graduate level course on quantum information processing. Normally it takes us about a full year to go through the canon of standard quantum mechanics kind of problems, and then even more in graduate school. But let's assume that we can skip all of that and distill all of the rules of quantum mechanics down into 2 rules. And I think we can do it, at least for the purposes of this next hour or so together, is to say that everything we need to know about quantum mechanics can really be said in 2 different principles. Right, so here are the 2 rules. Rule number 1, quantum objects can exist in multiple different configurations at the same time. And I know that sounds weird, but roll with it just for a minute, okay? We have quantum objects, and what's going to make them quantum by this rule number 1 is that we can have different configurations all existing simultaneously. So here's what I mean. Let me think about maybe an electron or some particle that can be a spin up or a spin down state. All right, so classically, we can say that this particle, here it is in the spin down state, and here it is in the spin up state. And that's all there is to the story. Quantum mechanically, this rule number 1 says that we can go a little bit further. We can say that this electron, which we might expect can be spin down or spin up, can simultaneously have some probability, some fraction of its probability being in the down state, and then 1 minus that fraction of being in the up state. So it is down and up at the same time. And if we can do that, we call such an object a qubit. Okay? This is a shortening of the word quantum bit, and it derives its idea from, in computing, we talk about a bit as being a 0 or a 1, or an on or an off, or an up or a down. It's a system that can be in 2 states, this or that. And quantum mechanically, we're now allowing the possibility that it can be this and that at the same time. All right. So if we think about expanding beyond just 1 qubit, all right, so let's say I have a whole collection of quantum bits, and I start thinking about all of the different configurations that these can perhaps exist in at the same time. Right? So here's a valid configuration, there's a valid configuration, there's a valid configuration, and the probability of being in all of these different configurations might exist all at the same time together. If you start to count up how many of them there are that can all exist at the same time, there are an exponentially large number of them. Okay? And exponentially large, this is really hard, I think, for humans to get our heads around. I'm really bad at it, personally. Thinking about exponential growth, I think, is one of the most difficult things for us to imagine. So if you've ever played that game of, I have a chessboard or something, and I put 1 penny on the first square, and then I double it, and now I have 2 pennies on the second square, and then 4 pennies on the third square, and I kind of keep going till the end of the chessboard. I can say it, and it's true, that you end up with more money that has ever been created in the universe by the time you get to square 64. It doesn't feel intuitive, but it's true, and that's an example of exponential growth. Right? This exponentially large number of configurations can exist if we just enumerate what are all of the possible configurations, and quantum allows us to be in all of them at the same time, right? And this exponentially large number of configurations, this at its core is what makes quantum powerful, okay? Access to all of these things simultaneously is not anything that we get in the classical world, and apparently in quantum, we can get it for free. So fantastic, that's rule number one. Rule number two is that rule number one only works if you don't look. Okay? Now, what do I mean by that? Let me make that a little bit more rigorous. So let's go back to this idea of a quantum bit, where I said that we have, let's say, a spin down state and a spin up state at the same time. Okay, so if we have this configuration, what I mean by looking is we go and perform a measurement, right? So I have a single electron in my lab, let's say, and I want to determine, is this system in the spin state up or down? Or maybe I see them both somehow at the same time, but that doesn't really feel right. So I make a measurement of this system, and what I find is some fraction f of the time, my measurement reveals the state down, and some fraction 1 minus f of the time, the measurement reveals the state up. And as soon as I've made a measurement of this system, what I have left over is no different than a classical bit. Okay, I've made this measurement. We're now in the state of down or up, just like things always were in the classical world, and this is the end result of my measurement. Okay, so when I say the previous rule only works if you don't look, what I mean rigorously is to say that these superpositions of states, this ability to have multiple states at the same time, only works up until a measurement is performed. Okay, now the catch. We require extreme isolation from surrounding environments in order to preserve these quantum mechanical properties, right? So I'm talking about a measurement here, but I also have to emphasize that measurements don't have to be performed by, me, the human experimenter, okay? So if I'm an electron and I'm in a spin down and spin up state at the same time, and a stray photon that I don't know about, a single particle of light comes along and interacts with that electron, or maybe there's a vibration, or maybe there's a background gas of oxygen or nitrogen that collides with that electron. From the electron's point of view, that counts as a measurement, whether I, the experimenter, wanted that to happen or not. And so we require this extreme isolation of quantum systems from their environment in order to preserve these quantum mechanical properties. Okay? And this is the core thing that makes quantum information science a challenging experimental endeavor to embark upon. All right, so we've got two rules. Objects can exist in superposition, only though as long as we don't look at the system, or only as long as we can keep it isolated from the outside world. All right, so that's a year and a half of quantum mechanics in 2 slides. So to put this in a little bit more context, I'd say that universal quantum computing is what I'd call the long-term holy grail of the entire field. And so I flashed the logos of a whole bunch of different companies up here. So major tech companies, Google and IBM and Intel and Microsoft and a number of different startup companies as well. They've all opened or are exclusively dedicated to this idea of building what I'm calling a universal quantum computer. Okay, and a universal quantum computer is just like a regular classical computer that you might be used to, in the sense that any problem that you can dream up, you can code it up, you can run that program on your quantum computer, and given enough time, you can expect that you have some output from that computer that solves your problem. All right, so this is a long-term goal of the field, is to try to build computers that make use of these additional quantum properties that I talked about on the previous slides. Now, I'd say that it's going to take a long time, I would say probably at least 10 years for this to be a fully realized thing, and that there are many near-term applications or nearer-term applications of quantum compared to having a universal quantum computer. So one is the ability to enhance the precision of measurements using laws of quantum mechanics. One is the ability to communicate securely between different parties, knowing for sure whether or not that channel is secure or not based on laws of quantum mechanics. And then another is quantum simulation, which is my own area of research interest, in which we use a very controllable quantum system in the lab, and we program it to mimic or emulate some other quantum system that's found in nature that we'd like to learn more about. And I think that it's immediately important to just ask this question of why quantum, right? Why are these companies investing billions of dollars, thousands of people, tens of thousands of people working their entire lives towards this kind of thing? What we have recognized over the past couple of decades is that certain computational problems that are out there are either provably known or at least strongly believed to be, I'm using this word, intractable, which really for the experts means that these problems scale exponentially or worse with system size. Okay, so there's that word exponential again, which is kind of a danger word when it comes to computational problems. What I mean by exponential is that, let's say I add one additional lattice site to a problem. I have 30, and now I make it 31. Exponential means for every additional, let's say, increase in particle number, I might need twice the computing power. And that gets a little dangerous, because as soon as, let's say, you max out the quantity, the capability of a supercomputer with some problem of a certain size, if I make the size just one bigger, now I need 2 supercomputers. If I add another one, now I need 4 supercomputers. And very, very quickly, we exhaust the entire computational resources of the planet, and we've only added a few extra sites. Okay, so certain problems are known to scale exponentially or worse with system size. Prime factorization is a prime example of one of these kinds of problems. Right? So if I asked you, what are the factors, the prime factors of 15? 3 times 5, easy. What are the prime factors of that number? Give you a couple of seconds, work it out in your head, maybe, right? Not a chance, okay? And of course, numbers even much, 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 much larger than this, it is known that as those numbers get larger and larger and larger, it takes exponentially longer and longer and longer to figure out what are the prime factors of those numbers. And we all use this, whether we know it or not, because the inability of factoring very, very large numbers into their prime components, this is what protects our credit card information on the internet. Right? This is the kind of thing that encrypts state secrets when we want to communicate securely. And being able to rely on the difficulty of factoring these large numbers is what protects a lot of these kinds of things that we want to keep secret. All right, so this is an example of a classically intractable problem. It's something that we expect that large classical computers, no matter how large we build them, no matter how many of them we build, we're not going to be able to solve that problem. Okay, here's another problem. This one comes from a more scientific background. This is materials and molecular dynamics. And so what I've written here is that the behavior of electrons in materials, the behavior of nuclei in molecules, all of these kinds of things, to be able to predict their behavior, again, requires exponential resources to calculate. And a lot of the prime importance of solving these kind of things are to develop new materials, to have the ability to, let's say, transmit power without loss, to be able to design new catalysts for more efficient chemical reactions, to design new drugs. Okay, so all of these kinds of things that we want to do as a technological society, often we run into these computing roadblocks because classically they're going to require exponential resources. All right, so we know all this about classical computing. And to me, kind of the amazing breakthrough is to say that quantum algorithms already exist that are known to efficiently solve these problems, and many others, of course. And what I mean by the algorithms already exist is that people know that if you use quantum logic, if you make use of these extra couple of rules that I introduced about quantum mechanics, namely the idea that things can be in superpositions of states all at the same time, you can use that extra technique to give a boost to the speed of your algorithms and break through that exponential barrier that we have classically and be able to solve them more efficiently if you can build the hardware to execute that quantum logic. All right? And so I think this is a strong motivation for the entire field of quantum information processing, which is to know that because these algorithms already exist, because we know that these quantum speedups are possible, now it becomes an engineering and a scientific and a physics challenge to actually build the devices to make use of that quantum logic. All right, so let me give you a very high-level overview of quantum information processing and the way that we think about things. So first of all, some good news. Good news is that what a quantum computer is really good at is processing on parallel inputs, right? And I mentioned that a quantum computer with n different, let's say, qubits in them can have 2 to the n, an exponential number of things in superposition at the same time. Right, so as an example, let's say that I have a 3 quantum bit system. And I start to count up what are all of the different configurations that my 3 quantum bit system can be in. 2 to the n, 2 cubed is 8 different possible configurations, and I've listed them all here. So this being a quantum system, we can build a system where all 8 of these possibilities exist simultaneously. That's rule number 1. All right, so what we can do is we can take this system and we can perform parallel processing on all 8 of these computational states at the same time, right? Great speed up. Some of the challenge, though, is that when we make a measurement of a quantum system, the measurement of that system, unfortunately, it gives a random result. And the random result is proportional to how much, what fraction of the state is in each of these configurations. And randomly, when we make a measurement, our system resorts back to a classical system, and we get only one of the outputs. And so this is the development of the entire field of quantum algorithms, which is to say, how do we translate, how do we make algorithms that have this random output and instead steer around this quantum state so that the output that we get, it depends on all the inputs, and the output that we get encodes the answer to our problem. All right, so all of what goes in the middle here are a sequence of quantum logic gates in analogy to classical logic gates, which allow us to manipulate the quantum state step by step by step along the way so that the output of this quantum measurement, it's not random, it's one that we dictate to be whatever it is as the answer to our problem. Okay, so the real hard part, the value added of quantum here, is that they have to be able to do something non-classical, right? So in order for these to really qualify as quantum logic gates, they have to do something that a classical logic gate can't do. Otherwise, it looks like a classical computer. And this is where we should think back to rule number 1 again, right? Quantum objects can exist in multiple different configurations at the same time, and that kernel of information, that key piece, is the thing that makes a quantum computer go. It is the thing that is different compared to classical, that greatly expands the power of what a quantum computer can do. And so what I'd like to do is to give you a little bit more of a feeling of something that is completely non-classical. And it sounds fantastic, but experiments like this have been performed many times, going all the way back to the 1960s, and not a single experiment has ever disagreed remarkably with what I'm about to kind of show you in a more casual form. So what I'd like to do is to think about a coin flip game. All right, so imagine that I have 2 coins, and I'm going to put them in a quantum superposition. All right, so I have my red coin and my blue coin, and I'm going to put them in this quantum superposition of both in heads and both in tails at the same time. Okay? And by now you're all experts at hearing rule number 1, that things can exist in superpositions if they're truly quantum, so that one shouldn't scare you anymore. Right? We have 2 coins, and they're both in heads and both in tails at the same time. So let's do a coin flip experiment to really see what that means. So I flip both of my coins, right? Or really, I give you one, and I keep one. And we go to separate rooms, and we agree, all right, exactly at 12 noon, we're both going to flip our coin. So we do that, and we write down what we get. All right, so I get heads, I write down a 1. You get whatever you get, it's heads, but I don't know that, you write down a 1. I flip them again. This time, I measure tails, I write down 0. You also measure tails, you write down 0. I flip again, I get tails, I write down 0. I flip again, I get heads, you also get heads. And I keep flipping, and I keep flipping, and I keep flipping, and I keep flipping, over and over and over again. And then later, we come back and we compare notes. What we've found is every time I flip a coin, whatever it is I measure, I don't know what it's going to be beforehand, right? Sometimes I get a 1, sometimes I get a 0. Sometimes I get a head, sometimes I get a tails. What I know for certain is that because these coins are entangled, whatever it is that I measure, you also measure. Okay? And we could be totally different rooms, different buildings apart. You could be on the moon, for all it matters, and we will absolutely always get the same thing over and over and over again. Okay? With no possible way of communicating between us. And if this sounds remarkable and even a little bit ridiculous, a lot of people have kind of questioned whether this can truly be the way that the universe is formed. In fact, Einstein very famously in 1930, amongst with some others, had a big paper saying, no, the universe absolutely could not behave this way. It doesn't make any sense for the universe to be this way. And it was only 30 and 40 and 50 years later where people continued to do theory and quantum information and then eventually experiments that demonstrated that, yes, actually, this is what is going on in quantum mechanics, and that you can have particles that are simultaneously in these multiple states at the same time, And then you can read out the correlations between these particles to demonstrate that, in fact, these particles are truly doing something not classical. Okay, so it's all of these kinds of additional techniques that we have in the quantum computing world that we can do something non-classical, and then that gives us additional power. All right, so I want to talk a little bit now about what it is that goes into building a quantum processor in the first place. Right, so again, if we think back to our rules, we need quantum objects which can be controlled to generate entanglement, something that can be used to generate these superpositions of multiple states at the same time. And whenever we think about quantum particles, sort of the intuition is you should think about really small things, really things down at the atomic scale, kind of like Feynman told us from the 1950s. So think things like single particles of light, which are photons. Think about atoms, think about electrons. These all make really good quantum particles. Okay, and in fact, in this kind of review article here, we have a whole bunch of different technology platforms that are currently used to host quantum systems. So we have individual atoms that are trapped using light. We have charged particles, which are ions, which I'll talk about quite a bit more in a little bit. We have superconducting systems that require going to really low temperature for the quantum behavior to show up. But all of these different kinds of hardware platforms are things that people are pursuing quantum computing in. All right, so in addition to having objects that can be in superposition, we also need objects that can be well isolated from sources of error. Right? These accidental measurements are the things that destroy the quantumness of our systems, and we want to make sure that we're limiting or eliminating these kinds of accidental measurements. And so for this, we use things like shielding, like moving to low temperature, like working in very high vacuum chambers, like going to systems with extraordinarily low vibration. So here's a picture from my lab. And I'll just kind of point out that in order to do these kinds of experiments, we have a whole variety of different laser systems for photoionization of the atoms and for cooling the atoms all the way down to almost absolute zero in temperature. And for manipulating the quantum states of the atoms and all of that, we have high vacuum chambers with electric fields that we apply to trap atoms inside of these vacuum chambers so that, again, they are absolutely isolated from everything else that's going on around them. Okay, and so if I were to zoom in on this vacuum chamber here, what you're looking at is a fabricated gold set of electrodes. So we can apply electric fields to these metal surfaces and use this to make a cage for charged particles inside of that field. Okay, and so here is a picture from what it is after we have confined a whole, so we've set up our entire system, we've got our lasers, we've got our electric fields, we've got our high vacuum chamber, we've got everything set up. We shoot a neutral beam of particles, of atoms, into our chamber. We shine on a photoionization laser to rip off one of the electrons and make this a charged particle. And as soon as it's a charged particle, that charged particle is held in place by the electric fields that we apply to those electrodes. And what we see is that. Right? So there on the screen is a single isolated atom that's trapped in my vacuum chamber in my lab. Okay? And so this is now relatively a routine thing for us to do in the ion trapping community. And the reason that you're able to take a look at this image of a single atom just confined in the middle of nothing, just glowing like a bright little star here, is the same reason that we can see stars in the first place. Okay? Light is scattering off of that object, and the scattered light from this single atom is being collected using a very big microscope objective and a very sensitive camera that's sensitive to only a handful of photons coming off of this atom. But there it is, and we can make images of it, and we can see it. All right, so when we have this apparatus in my lab, we have our vacuum chamber, we have the electrodes that we're applying our potentials to, and then inside here's a picture of, 10 or 13 or so trapped ytterbium-171 ions. And we've arranged the potentials so that they're all in a one-dimensional string with roughly 5 micron spacing between them. And you can see every single one of these atoms lined up here. Now, one of the questions that I often get is, why do you use ytterbium? And in fact, what is ytterbium and where is ytterbium on the periodic table? Right, so ytterbium, you might have to hunt for it for a while, but it's tucked away all the way down here in the lanthanide series. And part of the reason that we like using ytterbium for these experiments is because the lowest energy levels of ytterbium, they have this really nice structure where there are 2 isolated energy levels. They're split by about 12 gigahertz of energy. And these 2 isolated, very well-resolved energy levels are relatively immune to what's going on in the environment around them. Okay, so if the magnetic field or the electric field or those kinds of things are changing the environment around this atom doesn't care. The energy levels stay pretty much rock solid where they are. And this makes it a really well-isolated system, which is the thing that we need for quantum information processing. Right? We want systems that are immune to all the noise and stuff that's going on around them. And by the way, this kind of technology is what the official worldwide definition of the second is based off of. Okay, so the official atomic clock definitions are based on trapped ion systems where you have two separated energy levels that are extraordinarily well immune to everything else that's going on in their environment. So the same reasons that kind of define a second and make that a really good standard for timekeeping also make them a really good standard for quantum information processing. So one of the things that we've been pursuing in my own lab is to be able to manipulate the crystal geometry. So I've shown you these pictures of ions that we can trap in one-dimensional chains, but then we can also adjust what are the electric fields that are around these ions. And what that allows us to do is to transform these crystals from one dimension to zigzag to 3 dimensions to 2-dimensional geometries. So we can have all of these different lattice configurations for our trapped ions. And to be able to have all of these different lattice configurations for trapped ions makes them a really great candidate system for looking at the physics of a whole bunch of different types of, for instance, materials that can have the interesting physics happening in 1D planes or in 1D lines or 2-dimensional planes or 3-dimensional arrays. We can transform the ion geometry to more closely mimic the types of problems that we're interested in. Okay, and so here too, one of the strong components of what we're interested in are, this is for the experts a little bit, frustrated 2-dimensional systems that arise whenever you have 2-dimensional lattices with triangular lattice structure where it's impossible for local magnetic interactions to simultaneously satisfy all bonds. And so one of the things that we can do with these trapped ion crystals is to naturally let them form into these kind of triangular lattice arrays. And with these triangular lattice arrays, again, we have this nice platform for mimicking other systems that are out there in nature, except now we can control them in the laboratory and study them more directly. Okay, so in the last picture that I showed you, maybe this one right here, I've got a crystal of 29 ions in a 2-dimensional array. And I think it's always a worthwhile question to ask, in my lab, if I have 29 ions, is 29 ions a lot? How do we put this in context to say, should I be aiming for 30 and that's amazing, or was 10 already amazing, or do I need 10 million? Where are we? I want to return to this idea that if I have a collection of n particles, and each of these particles can be either in a spin down or spin up or some combination of the two at the same time, here's a valid configuration. There's a valid spin configuration, and in total, there are an exponential number, 2 to the n, valid spin configurations that you can enumerate. Now, in quantum mechanics, what we're often interested in is what's known as the wave function of this system, which really means we have 2 to the n configurations. We write down a set of 2 to the n complex numbers, which keeps track of what's the probability of being in any one of those 2 to the n configurations. Okay, so we have to keep track of all of those numbers at the same time. Now, just for a state of reference here, 29 spins, that's equivalent to 4 gigabytes of RAM. Okay, so that's something that my laptop can just kind of barely do, is to write down, just to keep track of what is the quantum state of 29 spins. And again, I'll remind you, 30 spins, that's 8 gigabytes of RAM. 31 is 16 gigabytes of RAM. You kind of see how this is starting to escalate real quickly here. Another point of reference is if I went up to 300 spins, I need more bits of RAM than the number of atoms in the universe. Right? So when I say that it is impossible to classically store these states, this is what I mean. Even if somehow you were to commandeer every single atom in the universe and use that to build your computer, you wouldn't have enough. All right. So these are all points of reference. And this is, so far, just to write down what is the state of a quantum system. And normally, we're not only interested in that in quantum mechanics. Okay? Normally, we want to say, I start the system in this state, and I want to know later on, what is the system state going to be? Right? So this is like saying, I've got a ball at the top of a ramp. That's the starting condition. And I want to know later, when it's at the bottom, how fast is it going, and how much energy does it have, and all that kind of stuff. Right? So what goes in the middle here, mathematically, is we have to write a big matrix to multiply this whole entire column of numbers. And if we think about how many numbers go into this matrix, I told you for 29 spins, right, there's 4 gigabytes of RAM per column here. And then we have something like 4 billion columns of this matrix. And so if you try to put this directly into a regular computer, even a supercomputer, it's much, much more likely that you're going to get an answer that looks like something like this rather than the answer that you're trying to get. Okay? There's just not the kind of computational resources available to my laptop, to my desktop, to anything that I have locally access to be able to solve problems, even at the 29 spin level. Okay? And so with this in mind, I want to really focus on what kinds of problems are out there that we are beginning to study using these kind of quantum systems that are historically inaccessible to classical systems. Right? And from my point of view, the best current applications of quantum systems are to study systems that occur in nature and largely are concentrated in chemistry and materials science. And so what I'd like to talk about a little bit is an experiment that we've done where we have emulated the behavior of hydrogen transfer systems, of proton transfer dynamics inside of a molecule using our quantum simulator. Okay, so let me talk about this. So first we have this molecule here, and the chemists love to put really big names on top of things, and here I'm going to call it the Begeman molecule, which is what they all call it for short. Okay, so we have this molecule here that contains a hydrogen bond system. Okay, so I've got a nitrogen here, and then there's a proton that gets transferred between those 2 nitrogen donor and acceptor sites. Right? And hydrogen transfer reactions, they are in all of us right now, happening 1 million times a second and all that. Life wouldn't exist without them. Okay, so this is one of those like super important biological things that you cannot get around. Right? Hydrogen transfer is out there, and explaining it from first principles, not able to do it using a classical computer. Right? Common theme here. So the experiment that we're looking at is to say, all right, if I have this proton that starts on the left side near this nitrogen, and I want to say, how does this proton transfer over to this nitrogen? What we can do is we can consider, well, there is some potential landscape for this proton to start on the left and to transfer over to the right. And there's a strong, even classical analogy here to say, if I imagine a bowl which has this dip, and then it comes up a little bit, and then a bowl again, and then a depression over here, and then it comes back to the other side. If I start the marble up really high, then it's going to roll and get over to the other side. But if I start it below this barrier, then it's never going to make it. Quantum mechanically, we know that things can exist in multiple different places at the same time, and so actually quantum mechanically, there's allowed this ability to tunnel through the barrier, and you still get transfer even if you start below the energy. And these are things that require solving the full quantum mechanical equations to figure out. Again, classically difficult to do. What experimenters can do when faced with a molecule, there's an entire field of chemical spectroscopy, is what they can do is shine in radiation of a whole bunch of different energies. And what they can look is how does this molecule absorb that sort of radiation. And this tells us something about the dynamics of the proton inside of the molecule. And this gives you some sort of an experimental signature of what's going on. What we would really like to do is to be able to understand these kind of molecules well enough that we can calculate these things from first principles. We can learn about all of the molecular properties from first principles without having to synthesize these molecules and test them in the lab and try to figure out what all their properties are, because these are the kinds of things that absolutely would accelerate drug discovery, vaccine discovery, all of these kinds of things where it is enormously computationally costly to do it. All right, so in this experiment, what I'm showing you here is what happens when we start this proton on the left side of this donor-acceptor system, and as a function of time moving downwards, the dark blue is where we are most likely to find that proton as a function of time. Right, so initially, if we started on the left, we see that proton starts on the left, then it bounces to the right, and then bounces to the left and to the right, and back and forth again. But we can also start it a little bit more towards the center, and we get a different oscillation pattern. And we can start it maybe in a superposition of the left state and also on the right state at the same time. Okay, you're all experts at rule number 1, so this is totally something we can do and can be seen in nature. We can also start it in what are known as stationary states, where we don't expect any time evolution. And in fact, whatever the original pattern is seems to persist as the pattern for the entire time of this experiment. And from these kinds of dynamics that we extract from our quantum computer, we can even go a step further and start asking, what is the frequency information in all of these vibrations? Right? For the engineers and the mathematicians and the physicists out there, we take a Fourier transform of all of these spectra. And taking the Fourier transform exactly reveals what are all of the frequency components that go into all of these oscillations. And so all of the peaks that you see on the right-hand side here, these are the peaks calculated from our quantum computer. All of the vertical dashed gray lines, these are peaks that we calculate from first principles using a classical computer. Okay, we picked a molecule where we can do it both ways, and the result of the quantum computer absolutely lines up to as well as our experimental precision can handle in agreement with what we find classically. Right? So this is a fantastic validation of the methods that we're using in quantum computation to learn something about molecules. Going a little bit further, I also want to touch on materials science. So in this case, I have a system of, let's say, interacting magnetic spins, right? And I know that a lot of the faculty in the physics department work with interacting magnetic systems. And so in this case, I've written a system where there is a little bit of competition, okay? And the competition comes from the idea that this part of the system really strongly prefers neighboring spins to point opposite to each other. And this part of the energetics really strongly prefers all of the spins to point in the same direction as each other. Okay, and so those two pieces together make this competition. And so we can do an experiment to say which of them wins out as a function of which piece of this energetics is more strong than the other piece. Okay, so here's an experiment where as a function of the strength of this part compared to this part, we look and ask, what is the state of the system in its lowest energy configuration? And we can scan all the way through all of these different states, and it turns out to have this really nice staircase structure. And we can, using our quantum system, figure out something about the material science of this magnetic spin system. One of the final things that I'd like to show in terms of the experiments that we can do, again, involves a magnetic spin system, where in this case, we're looking at magnetic fields that are pointed differently to the way that these spins like to interact and align with each other. And what we're doing is we're taking a look to say, what are the longest systems where we get kind of these uninterrupted chains of spins in the spin-up state. And we do this as a function of the external magnetic field, and we kind of figure out statistically what are the number of the histogram of the number of occurrences as a function of what is the longest in an uninterrupted chain that we're seeing. Right? And calculating these kinds of things can predict the dynamics of phase transitions. The problem is with systems this large, you can't calculate them. Because for 53 spins, this is a much larger system than you can feed into a classical computer and come out with these kinds of results. And so for my money, this is the kind of experiment where, this is the first to my knowledge, where we have an experiment where the system itself is too large to calculate classically. Okay, so this is an example of doing a quantum computation of some material science question where we had no other way to do it, and we built a quantum system to look like another quantum system. We controlled it, and then the answer that we got out of our quantum system is telling us something about the system of interest. Right, so to start thinking a little bit towards the future, I do want to say a couple of words about where I see things going. Right, so I'd say for me, in the near term, where we are now and over the next few years, absolutely the kind of greatest hits of quantum are going to be in quantum simulation. So I've talked a bit about using quantum systems to learn about other systems in nature. I haven't talked too much about quantum sensing and communication, but all of these together, these are kind of at the scale of tens to hundreds of qubits. So this is where we are now in my lab. This is where we are in ion traps and other kinds of quantum platforms around the country, is at the tens to hundreds of qubits level. And we're already able to do things that are difficult, if not impossible, for even supercomputers to do currently in these kinds of regimes. And so two things that I'll talk about just kind of very quickly. Here, this is gravitational wave observatory. Okay, so the LIGO experiment is a very large collaboration that is able to see the gravitational signature of large astrophysical events, black hole mergers and neutron stars and all these kinds of things, and the changes in gravitational waves that are passing through the Earth as a result of all of these astrophysical dynamics. And The sensitivity of these devices in upgraded versions of these kinds of interferometers is being driven by quantum sensing, okay? Cooling down mirrors and parts of their apparatus into quantum states so that they can get a higher precision than you can get classically. And this is an example slide of one of the more recent developments in quantum communication, where people have been able to securely send information between places in Austria and China and up through satellites, all using entangled photon pairs, where you can carry the quantum information signal and make sure that it is secure against eavesdropping, because you'll have an immediate signature. As soon as somebody looks and measures your quantum system, then you're going to know about that immediately. Right. Very far term, I think we can recognize this, this long-term goal of the field, which is this universal fault-tolerant quantum computing. So this is the idea where it's going to be millions of qubits, and the applications of this will indeed be things like factoring of cryptosystems and database search and optimization problems and all of these logistics kinds of problems, where we are certainly doing universal computation. We program in the kinds of problems that are currently difficult for classical computers, and we have the algorithms already in hand to execute on this quantum hardware so that we can really push things forward. And so to summarize, what I've shown you is that quantum systems can exploit this key idea of entanglement, this ability for quantum systems to be in multiple states at the same time to do something that classical cannot do. Right? So already, I've shown you some examples of quantum devices that have performed calculations that are inaccessible to classical computers. And I think in the near term, our applications in material systems and chemical systems or analog systems like that are the most likely to make headlines. And then certainly in the long term, I think a lot of these generalized quantum computing and computer science problems are going to be there to be solved as well. Thank you so much for your attention, and I'm happy to take questions.
All right, there are microphones in the aisles, and so I would appreciate it if you use the microphones to ask your questions. So, floor is open.
Thank you very much. One of the applications is in materials, right? I read a couple of books, and mostly talks about drugs, right? So medicine and like medical applications and these kind of things. So other than medical applications, what other materials may be simulated using quantum?
Yeah, so I think that, so the question is, what other materials? I really do think that systems with lots of entanglement, systems with long-range interactions, frustrated systems or systems with frustrated ground states, these are all probably the best application of quantum systems, right? And so, I know that you think about DFT and all of these things. I would say, what are the kinds of systems that are difficult for DFT, right? And we've talked about those a little bit. Things with long-range interactions, things with tons of entanglement in them, things where you cannot chop the unit cell to be small enough to fit in your... I think these are absolutely the best applications of these kinds of quantum devices.
I'm a computer scientist at heart, so I have a lot of questions. But to start off, so at the beginning of the talk, you talked about extreme isolation.
Mm-hmm.
So I often think of like the early days of computing, we had to deal with error correction, especially in the networking space. Hamming codes came up as a way to correct bit changes or blip flips that might have happened as part of the transfer process. Is there research being done on how to do that with like quantum misreads or stuff, something like that? Or if we observe something and it wasn't the correct result, what is the error correcting that we can?
Yeah, absolutely. So it's a great question, and it's the question of what happens when there's an error. And in fact, I have to say that in the early days of quantum information, this was a big concern of a lot of people, and there were many people, famous people who publicly said quantum computing will never work. Exactly because of this reason. And maybe to be more specific, it's the idea that a quantum system has this exponential configuration space that it deals with. And if you have an error, it seems almost impossible to say, how can you ever find and control this exponential number of things perfectly with no error? And so, if any error happens, you're never going to know about it, and the whole system is unsalvageable. The invention of quantum error correction, I'd say, is what silenced all of those skeptics. And quantum error correction, it relies on the same, I'd say, very core principles as classical error correction, in the sense that at the end of the day, you are taking things that look like majority votes or Hamming codes, and you can concatenate codes to say that with extra overhead of bits, or in this case qubits, that you can have redundancy in systems and you can protect systems against accidental bit flips or errors or that might come in. The difficulty in quantum error correction is related to this rule number 2, which is that you're not allowed to look at a quantum system in the middle of a computation because that counts as a measurement. And so how do you know an error has happened if you're not allowed to look at the system to know if an error has happened? And it's amazing to me that people have figured out a way to do this, but people have figured out kind of almost a backdoor hack, I could call it, to a quantum system to accomplish this directly. And what they can do is to say, let's imagine I have some lattice of quantum particles, and instead of just saying, did this particle have an error on it, I can measure, did this collection of this one, this one, this one, and this one all together, is there an error somewhere in that area? Okay? And the answer might be yes or no. And if the answer is yes, then I can ask, well, what about this area over here, which includes some of the quantum bits from over here? Yes or no? And what about this area over here? Yes or no? And by asking a bunch of these yes or no questions, you can intuit which one had to have the error without measuring it directly. Yes. That's right. So I think a lot of that fundamental spirit is what motivated the development of quantum error correction. And absolutely, this is the kind of thing that people think is going to be crucial for scaling computers to quantum computers to millions of bits and all. Without error correction, it almost certainly won't happen.
All right, so yeah, I'm also a computer science major as well. So knowing that the complexity of how this quantum computer can hold in terms of potential, especially in encryption, I have my curiosity that if quantum computing can resolve problems which requires encryption for prime numbers such as that, would we need a new way for encryption for data? Because quantum computers might have the potential to break it down, or should we allow a new kind of algorithm that serves like anti-quantum computer?
Yeah, so in fact, this is something very much of interest to NIST in the US, who is kind of dedicated, part of their mission is to guarantee the protection of cryptographic standards in the US. And one of the things that they are very much engaged with is this idea of so-called post-quantum cryptography. In other words, what are the types of ways that you can think about, let's say, public key cryptosystems, which don't rely on the security of information being protected by the inability of factoring large numbers? In other words, are there different ways of encoding information that are still public key, but also are immune to these kinds of attacks from quantum computers? And this is very much a hotly debated subject. People are thinking about it very strongly. And in a way, I also like to point out that when it comes to secure communication, what quantum takes away with these factoring algorithms, it also provides with brand new types of secure communication algorithms where you and I, let's say, can set up a secure quantum channel. And if anybody else tries to eavesdrop on that channel, then in a way, this kind of counts as a measurement of that channel. And we can check to see, has anybody else measured this signal between us? And of course, if the answer is yes, and we suspect an eavesdropper, then we stop and we set up a new channel. And so there are ways of also communicating which are quantum secure at the same time that we also have quantum ways of breaking existing cryptography.
Hi, good evening. My name is Dylan Carlson. I'm a history major here to support my roommate tonight. But my question for you is, well, first I'd say that was an awesome presentation, very interesting. But you mentioned the DoD at the beginning, the Department of Defense, and how they're interested in quantum computing. I would assume it has something to do with the NIST and the cryptology aspect as far as defensive stuff. But what other projects would they be interested in quantum computing?
Yeah, so I think a lot of the, so as a very generic level, kind of there is an entire division of DoD that is dedicated to new materials, and I'm starting with that one just because I can kind of point to pictures like this. And new materials are great. New materials are things that enable faster and lighter and stronger and lower power and lower heat loss and all of these kinds of things, which find their way into submarines and fighter jets and everything else the DoD is involved with. But I'd say even more generally, beyond things like computations specifically, something like, let's say you're a submarine and you don't want to give away your position. So you want to stay underwater for 6 months. And you also want to know where you are without coming up to the surface and beaming up and getting a GPS signal or anything else. This requires really precision timekeeping. Okay, so inertial navigation kind of requires you to have an excellent onboard clock to sort of match your velocity, and you know how much time has passed, and then you can kind of exactly figure out where you are without needing to reference anything else. And so something like the technology behind quantum computers is also exactly the same kind of precision timekeeping instrumentation that can then be miniaturized and then made portable and all of this sort of thing. So developments in quantum information processing have then coupled forward into things like precision metrology and precision sensing. So there is a large effort in DoD for that as well.
Phil, why are Wall Street companies interested in this technology?
Yeah, why are Wall Street companies interested? So Wall Street in general tends to be, so there's kind of two reasons depending on how in the weeds we want to get about it. But in general, there are kind of classes of making money, which involve so-called portfolio optimization, right? I have a whole bunch of different things, and they all have different risk profiles, and they all have different correlations with each other. And you can imagine this as being some one big correlated system. And what you're looking to do is to, let's say, maximize your return, right? What's going to make you the most money per unit of risk that you are willing to invest. And finding that optimization is not always an easy thing. And in fact, it's kind of known to be a difficult and intractable problem classically. And if quantum computers can figure out a way of navigating that very complex landscape and finding what is the optimal solution or the near optimal solution, then this can be an advantage to Wall Street companies.
Another very quick question. So you mentioned that one of the main applications of, in terms of material science, is study of frustrated systems. So can you give a few examples, like what kind of frustrated systems we're talking about? I mean, it's like magnetic frustrations,
Yeah, so I'm thinking, in particular, magnetic frustrated systems, and at least for me personally, I think the high TC problem, it hasn't really gone away. People can make high temperature superconductors, but explaining them from first principles and saying what is the underlying Hamiltonian or what is the underlying model that kind of describes this sort of thing. What we would love to do in these kind of quantum simulator devices is to say, have a theorist say, I think this is the explanation for high temperature superconductivity, but I can't do a large enough system classically to demonstrate that. And we say, that's fine. We're going to take that Hamiltonian, we're going to program it into the system of 1,000 or 10,000 or something, interacting spins, and we're going to see if we see these signatures or not.
So you spoke about these simulation systems, and I saw some applications of spectroscopy, and I was wondering, with these sort of simulations, would you be able to limit it sort of like computationally heavy parts of spectroscopy that usually take a lot of experimental values, such as fingerprint regions and whatnot?
Yeah, so I think that is entirely, a lot of the motivation behind it, right? Which is to say, in the early days, let's make sure that the quantum simulator is doing the correct thing, right? Let's take experimental data from known molecules, let's calculate them from first principles, and let's compare everything together to make sure everything all agrees. And once we've built confidence in the system, like which we've kind of already taken the first steps to doing that, then we can start to say, if we have this brand new molecule that's never been synthesized even, can we still from first principles calculate what it's going to be, what its spectrum is going to be, and how it's going to behave? And we would love for the answer to be yes, because it's extraordinarily difficult and costly to synthesize a whole bunch of new molecules, new drugs, new everything else, just to see which ones work and test what their properties are. So absolutely, that's one of the long-term goals.
Thank you.
My question was like, how do we mathematically represent like a qubit system? And since you mentioned, like it simultaneously exists, like it's not an on and off. So can we like, how can we like track like the entanglement?
Mathematically or in reality?
Mathematically.
So mathematically, in order to kind of track what happens, you have to sort of at all times account for every possible configuration that the system can be in, and what are the sort of the probabilities of being in all of those configurations at the same time. And this is why it's so so numerically costly to do it. So this is why, for 29 spins, it takes 4 gigabytes of RAM at any time slice just to say, where is the probability at that point in time? So tracking it is very expensive from a resource point of view, but it has to be done. Somehow in nature, nature has figured out how to track all of these things at the same time. But if we want to express it mathematically or inside of a computer, it's going to cost us.
Yeah.
Mm-hmm.
I have a more of a generalized question. If somebody were interested in like pursuing this in like undergrad here, more likely in the medical aspect, what are some project ideas that you would recommend?
Some
Project ideas?
project ideas that you recommend. So I know that in meeting with a number of faculty, that there are a number of different, projects in experimental and theoretical physics that are starting, especially on the magnetic materials side of this, to have strong overlaps with what I've talked about here. And sort of from the material science point of view, figuring out the way that materials interact with each other and the way that you have a lot of material properties that can kind of only be understood by explaining what are the quantum interactions between these particles. We can understand that from a high level, and I think that there are a lot of projects here that are looking to do that and involve lots of undergraduate students to do that. And then being able to get control over the single particle level is sort of the next step after that to say, all right, we can, how do we then start to program these kinds of materials to look like other things that we might be interested in too?
Hello again. So as a programmer, we often work in layers of abstraction, right? So at the beginning, we have assembly language. On top of that, we have our lower level languages like C, C++. On top of those, we may have our higher level abstraction layers, Java, C#, and then we have like our absolute highest, like Python. I know Open Quantum assembly language is a thing. I haven't heard any talk about like higher level quantum computer science language or computer languages. And also additionally, I think that there's, problems that maybe classical systems are better at from a computational perspective than, qubits or quantum QPUs would be good at, right? So as these systems become more commercially viable and are offered, and I'm a developer, I'm lazy, I don't want to have to develop an open quasm. Is there research being done on how we can analyze source code to be more optimized for our quantum qubits as well as our more classical CPUs?
Yeah, right. So it's a great question, and I have to say that I'd say in the development of the full quantum stack, there are a lot of people who are thinking about it. I'm involved in a couple of efforts to do this as well, but I think we all would acknowledge at some level, we're laying the groundwork, but I think it's a little bit premature. And I say that because, at the beginning, I flashed up the logos of a bunch of different companies, Microsoft and Intel and Google and IonQ and Quantinuum and all of these kinds of things. And, I just listed 4 or 5 companies, but also they are involved with probably about 4 or 5 different fundamental quantum platforms to host all of the kinds of very high-level abstract gates that you might write. So if you write, I want to perform a quantum operation that entangles this qubit with that qubit. That's great from a very high-level abstraction layer, but as you dig down in the code just a little bit, the physical things that are getting done very quickly diverge from each other. So in my system, it might be I shine a laser beam onto that ion and that ion for a certain amount of time, and then that entangles them. Whereas in some other platform, it might be, I send a microwave down this signal line in a dilution refrigerator to a special chip, and that entangles just these two. And then I have to swap the entanglement from these two to those two, and then those two to those two, and those two to those two. And so what happens under the hood is wildly different. And I'd say it's good in the sense from a development point of view that we don't expect or even necessarily think it's a good idea that high-level developers know the dirt and the details about what's going on, inside the QPU. But certainly without knowing exactly what the compilation target is, it's hard for the compiler to be efficient about it.
Speaking about efficiency, and I get that we're in the R&D stage of this and these are in university labs, but what's the energy, the good old-fashioned electrical energy cost to run a quantum computer versus a classical computer? And is there a future which we carry around quantum computers, or are they too specialized and need to be in too isolated an environment?
Yeah, so it's a good question. I know that there are examples of portable quantum, let me call them portable quantum devices. Okay, and in fact, there are companies that make sort of certified random number generators that are based on quantum superpositions. And they're little device kind of things that you can put in your pocket. They're not fully fledged computers, but they're quantum devices. I think, will we have the example of a quantum phone or something else like this? I think it's going to be a question of, are there problems that the everyday person would find advantageous to solve in a quantum way that is useful for them to have with them? And if the answer is yes, then I'd expect that, sure, there's a market for it, and then the technology will be pushed, and eventually we'll see it. Honestly, for me, it's a little hard to envision that right now, just from the point of view of, we have these massively powerful classical computers, right, supercomputers and all that, but we deal with them in a very cloud-based way, right? And these are specialized and for scientists or for big data or for something like that, where, we send a command and then we wait a week and then we get a result back. And I think that the quantum computing model is probably going to be much more in that vein for a long while.
I have another question. Why is generating genuinely random numbers important? I heard a news item about it a couple of weeks ago, I think, from one of these Wall Street companies.
Yeah, so let me give like a serious answer and then a fun answer, right? So a serious answer is let's go back to cryptography, right? So if you want to protect your credit card information, if you want to protect some important secret, then in some level you need a certified random number or a really good random number so that you can kind of seed an algorithm for generating that cryptosystem, right? So if you have, let's say, a flaw in a random number generator, so you think you're generating random numbers, but I can pick up what pattern it is that you're really using to generate, then what you're securing with that random number generator isn't really secure anymore, okay? So that's kind of the serious one. And maybe the less serious one, but also, I don't know, involved with a lot of money, is random number generators are inside of things like slot machines in Vegas casinos, okay? And so if somebody were able to figure out, nope, that's not truly a random number, and if I can figure out what algorithm is used to predict the next random number, then I know exactly what slot machine to play.
You spend a lot of time in Vegas, right?
That's right. I'm still trying.
Other questions?
What is the primary constraints with the hardware right now that only allows you to do tens or hundreds of qubits, and how do you anticipate that's changing over the next few years?
Yeah, so let me talk specifically about ions, because that's sort of where the roadmap is a little bit clearest, I think. So right now, collections of tens or 100 ions, the limitation here is, I'd say, the amount of control you have over that many particles inside of one of these electric field type traps. Right? So we have to have ways of confining these ions, and we do that with electric fields. But there are always unwanted sources of noise which affect the confinement itself. Okay? And these are even a handful of stray electrons that have found their way to some surface somewhere that you don't want and you don't know about potentially. They can disturb at a very small level the types of interactions that you're generating in traps. Once you move much beyond 100, then it's really hard to get very high fidelity operations. And so the sort of the roadmap of how to go beyond that is to say, okay, we can build these really good traps with 100 qubits inside of them. And Imagine then you had a set of traps. Each of them is really good with 100 qubits each, and you network them together using entangled photons. Okay, and so this is a huge area of research. This is kind of what many of the ion trap quantum computing companies, these billion-dollar companies are banking on, is this idea that you can take photons, you can make those photons interact with some of the ions in this trap, and the entanglement that's in this trap is then transferred to the photons, which can then travel through a fiber. And the other end of that fiber can be plugged into a trap, maybe a millimeter away, and now you have 200 qubits that are networked together. Or maybe it doesn't even have to be a millimeter away. Maybe it could be in the next room or the next city. You can now start to get this distributed network of individual traps of 100 particles, and now it's a question of how well can you fabricate these traps, and can you make this kind of fabrication at scale, and all of these kind of classical fabrication questions, which, by the way, the whole entire silicon industry and photonics industry knows how to do really well. So I think that's the most kind of promising roadmap to scaling up, but people actually have to do it, I think, for everyone to believe it.
Last one, I promise. So at the one point you talked about interactability. In my world, I think of it as like, the hardness of a problem.
Sure.
And so a big classical theoretical computer science problem is P versus NP. Does P equals NP? Otherwise known as, does the verifiability of a problem equal the ability to solve it in that same time? I feel like quantum computations kind of throw a wrench in that whole entire premise of that understanding, because the way that we're computing the answer completely changes. So how does quantum computing mesh with theoretical computer science and change our understanding of polynomial time solving versus exponential time solving?
Yeah, so I think that the best way, and I don't know if you know the computer scientist Scott Aronson, but he's talked about this a bit. And I really like his framing of it, which is essentially there's three options. So one, in computer science, we're taught about the strong version of the Church-Turing thesis, which tells us that any physical process that is going on in nature is something that can be efficiently, classically replicated on kind of an ordinary computer, if you want to call it that. So that's one possibility, right? Which is to say, quantum mechanics says everything I've presented here, it throws a wrench into it. So it could be that the Church-Turing thesis is wrong because of everything that I've just said, and that is my belief, right? But it's a possibility that it's right, which means something else is wrong. And that something else could be either that quantum mechanics is wrong, okay? Quantum mechanics is missing something fundamental in our theory right now, right? So I have to say, I thought that when I was first learning quantum mechanics, it sounded a little bit far-fetched and ridiculous. And then over time, once you get used to it, once you see the extraordinary amount of experimental evidence that people just like me have been trying to poke all of these holes in it since the 1930s, and every single person who's tried has come up empty, okay, maybe there's some merit to it, but also maybe there's something else that somebody hasn't poked that makes quantum mechanics wrong. Maybe when we get to systems of 300 particles, the Schrodinger equation doesn't work, right? I don't know. That's never been tested. It could be. That's possibility 2. And possibility 3 is that the entire polynomial hierarchy collapses. The problems that we think are hard are not really that hard, and the problems that we think are easy are actually harder than the problems we think are, the whole thing. So one of those 3 has to be wrong.
Hi, I'm an undergraduate biology student, and everything you're talking about sounds pretty expensive. How do you get to the point where you're starting a lab to visualize these atoms? How do you build up the funding and the education level to get where you are now?
Yeah, so I'd say that this is one of these stories where I kind of mentioned that the development of atomic clocks has been going on for about 30 years or so. And I think this would be a fantastical amount of work that would happen in a single lab over a few years. And we are relying very heavily upon this long history of investment and expertise in the field of making really good, really good precision isolated things, which then later turned out to be really good for quantum computing. And so to kind of get to this point, it's the sort of thing where, I sort of joke with my students that when they come in and they do their calibrations in the morning, right, they isolate a quantum bit, a trapped ion. They take that isolated thing and then they cool it to, a fraction, 500 microkelvin, just barely above absolute zero. And then they initialize it in some state, and then they put it in these superposition states and then these entangled states. Like every single one of the things that we do before 10 a.m. at some point in history was a Nobel Prize. And now we just kind of take it for granted because it's so useful and so well understood that it's now at the level of a calibration for us. So I'd say it's a lot of expertise, but also built up over decades of work.
What are the advantages of trapped ions versus some of the other platforms?
So one of the things that I really like about trapped, of course, I have to be the salesman for trapped ions, right? I am legally obligated to do this. But I think one of the really nice things about trapped ions is, so far as we can tell, everywhere in the universe, every single species of atom is identical to every other atom of that species. Okay, so if I just think about hydrogen, then a single hydrogen atom, in the sun is the same as a single hydrogen atom somewhere in my fingertip, is the same as a single hydrogen atom halfway across the galaxy, right? In every possible way, in mass, in the charges of its constituents, in the energy levels, in all of it. And that means that when I'm thinking about building a quantum system, and I'm thinking about, I need this qubit to be identical to that qubit, to be identical to that qubit, then whenever I'm dealing with atomic systems, I have that all built in for free. And that's not something that you get man-made, no matter how hard you try. Right? So if you're building a superconducting system or a quantum dot system or anything that's in a bulk material, you always have to worry about this so-called calibration issue, where if I have 1 million qubits and their energy levels are all a little bit different because they've all been made in some man-made fabrication process and there's a little bit of dirt or dislocation or something at the microscopic scale, you have to calibrate for that. You have to worry about it, and then that itself turns into its own exponential headache. So I think that's one of the strong long-term advantages of ions.
I know Quantinuum uses trapped ions.
Yes.
What about some of the other companies?
I'd say Quantinuum and IonQ are the big companies that use ions. I'd say the large tech companies, for different historical and political reasons, have chosen different platforms.
I'm a chemistry student, and I'm very clearly out of my depth. But I'm confused about what exactly a qubit is. You keep mentioning trapped ions.
Mm-hmm.
Is the qubit itself the ion? And of course, I'm familiar with spin slightly. Is that a property of the ion's electrons or the ion itself?
Yeah, great question. So what I would say is that the trapped ion hosts a qubit, and the qubit itself is what is the spin configuration of the outermost, so in the ytterbium-171 ion, the valence shell has a single electron in its s state, okay? Just like hydrogen. There's a bunch of inner shell electrons, because there's a ton of them in ytterbium, but the outer valence shell is a single electron in the s state, and whether that electron spin is spin up or spin down is the qubit.
So would that limit you to using ions with only one electron in its outer valence shell?
Yeah, so let me see if I can do this quickly. There are a lot of slides here. But there are other choices of ions that are common in the community. And ytterbium is one choice, but there are a whole bunch of others. So here's the periodic table. And far and away the most popular ions that are chosen for doing quantum computation kinds of things, they all live in this group 2. And the reason is that when you ionize these group 2, then you end up with a single electron left in the s shell. Okay, so beryllium, I mentioned NIST a couple of times here. Beryllium is used by NIST, although they've also used magnesium. Calcium is used in a couple of places in California and also in Austria. Strontium is something that I used in an undergrad at MIT. Barium is now coming into favor. That's used in Waterloo and also at Quantinuum. So all of these kinds of group 2 elements, when you ionize them and they have a single electron in the s state, they make fantastic qubit candidates.
Just to let you know you're not out of your depth.
Hi, so many current quantum computing architectures rely on superconducting qubits or trapped ions. Do you see a future where we move beyond these to an entirely new like paradigm, possibly even like biological quantum computing?
Yeah, so I think the only things from my point of view that a quantum bit or a quantum computer has to have is some way of creating these entangled states, some way of isolating them from the environment, and then some way of doing kind of, let me call it, traditional programming of some kind. You want to be able to initialize it and manipulate it and then read it out at the end like a normal computer. If you can do that, then I think any platform is up for grabs. And I wouldn't be surprised, I have to say, if there is some unknown platform right now that totally takes over compared to ions or superconductors, right? So I do often tell people that, we might be in the kind of the vacuum tube equivalent of classical computing, where the transistor isn't invented yet, or if it's invented, I don't know if you've seen pictures of the first transistor, but it's about this big and it looks like it's put together with glue and paper clips. And to think, yeah, that thing, we're going to put 1 billion of them on the size of a postage stamp, impossible. Turns out that we figured out how to do it because that was, a fantastic way forward compared to vacuum tubes. That equivalent might still exist for qubits. I don't know what it is, but there is absolutely that possibility.
Hello. So currently, obviously, we're using quantum systems in the world of medicines for MRI, gene sequencing, just about everything. But as we learn more about quantum systems as a whole, where do you see the future of modern medicine kind of integrating itself with quantum systems?
I think that I see quantum in maybe 2 different ways. So there's the computational way, and kind of the standard things that we like to talk about are things like drug discovery and being able to have targeted drugs for particular, maybe diseases or maybe even particular patients. I'm getting a little out of my depth with that, but people talk about that and being able to design them, kind of these bespoke molecules. Well, if you can calculate all of its properties and you can do it efficiently, then why not? So that's one aspect. But then the other aspect might have to do a little bit more on the quantum sensing side. And I didn't talk about it too much, but there are the possibilities to have sensors where the sensitivity is enhanced by the ability to have entangled quantum states. And in particular, if you can kind of deliver a set of entangled quantum states kind of nearby some object, then it can make a much more sensitive probe of things like electric fields or magnetic fields or other kinds of things. And so people very seriously are talking about taking little materials, they're actually little pieces of diamond which have these little qubits inside of them, and make them at the nanoscale and maybe put them in a pill or something else that you can either swallow or maybe inject to a certain site and get sensitivity to some biological action which is happening inside of a person, and use that as some sort of an enhanced diagnostic. So it's a little bit futuristic, but I wouldn't be surprised if something like that is something we see soon.
So there's been some already discussion about using quantum information within communication, and with how we'd be able to detect if kind of an outside party were to make a measurement of the channel and how we would be able to close that. But we also talked a bit about how in order for error detection or error correction to occur, we'd be able to kind of check areas of a message.
Yes. Okay, so here's a difference. But go ahead.
Yeah, I was just wondering, would there be a possible concern in the future?
Yeah, right. So I think the difference has to do with the ability to check all simultaneously, like you might have in a real, let's say you had a big array of quantum bits where you're doing your computation, and then you have the ability to simultaneously check a whole bunch of them at once. And that simultaneous is important, okay? So you have access to the entire system. Let's say if you're doing a quantum computation and you want to do error correction, you can see the entire system, and then you can make measurements locally on this section and that section and that section and that section. Okay? The simultaneity is important there. If I were to be securely communicating with you, in contrast, presumably I would be sending sort of one quantum bit at a time. And some eavesdropper then would not have simultaneous access to multiple qubits all at once, and then could then use those kind of protocols to sort of do that simultaneous measurement. So just in the time dependence of the transmission of the communication signal, that problem is set up from the beginning to be a little bit different than an error correction problem.
Thank you.
was wondering, you were talking about when you had like hundreds of qubit systems and communicating them. You specifically said you could use photons.
Yes.
To do it. I was wondering, if you could entangle two qubits and have them separate from the computer, why not transfer information that way through like a Morse code sort of thing? Yeah,
and so I have to say that, so there are two ion trap companies, that are kind of most well known, IonQ and Quantinuum. IonQ talks very much about this photonic interconnect. And I'd say for the medium term, Quantinuum talks much more about something that you're suggesting. And this is called kind of a quantum charge-coupled device architecture. And it makes analogies to the way that kind of CCD cameras in your phone or anywhere else work, where you can kind of imagine this pixel array, and then these things kind of get shifted in time, and you read out signals this way. Here in this architecture that Quantinuum is doing, they have, let's say, a trap of 100 here, and then on the same chip, another trap of 100 here, and then down here, another trap of 100. And so you can entangle a bunch here and here and here, and then you can shuttle ions from here over down to this one and spread entanglement, and then shuttle ions from this one down to that one and spread the entanglement. And you can go as large as the, kind of the size of the trap that you can physically manufacture. And honestly, I think that that's going to be a good medium-term approach of going from, let's say, 100 qubits to 1,000 or maybe 10,000. But then when we start to talk about 1 million and 1 billion, I still think that some level of photonic interconnect is going to be necessary.
Well, if there are no other questions, let's thank the speaker again for a wonderful presentation. Feel free to come forward and speak to Dr. Resherm individually if you wish.